Have you ever wondered what's hidden beneath the swirling clouds of Jupiter and Saturn, the gas giants of our solar system? These colossal planets, with their churning atmospheres and breathtakingly enormous size, have long captivated our curiosity and bewilderment. Gas giants, as their name suggests, are primarily composed of hydrogen and helium, the very same elements that fuel the stars. Despite their vast size, these planets are largely enigmatic, shrouded in a veil of mystery that scientists are striving to lift. Beneath their turbulent, storm-ridden atmospheres, what secrets do they hold? How were these gigantic bodies formed, and how have they evolved over billions of years? Answering these questions isn't just about satisfying our curiosity, it's about understanding the fundamental processes that govern our universe and our place within it. To understand more, scientists have to delve deep into the heart of these gas giants, a task easier said than done. So, how do scientists peer into the heart of these enormous planets? It starts with the basic yet indispensable tool, the telescope. These instruments, whether based on Earth or floating in the void of space, are the eyes that allow us to peer into the cosmos. They detect light across various wavelengths, from visible light to radio waves, and even X-rays. Each wavelength provides a unique perspective, revealing different layers and characteristics of the gas giants. Next, we have the spacecraft. These are the scouts of our cosmic exploration. The likes of Voyager, Galileo, and Juno have journeyed to the gas giants, bravely venturing where no man could. Voyager, launched in the late 70s, provided the first detailed images of Jupiter and Saturn. Then came Galileo in the 90s, orbiting Jupiter and plunging into its atmosphere to send back first-hand data. Most recently, Juno has been orbiting Jupiter, probing its magnetic field and scrutinizing its swirling storms. But there's a limit to what we can physically observe. That's where computer simulations come in. Scientists use the data gathered from telescopes and spacecraft to feed into complex models. These simulations allow them to recreate the conditions within gas giants right here on Earth. They can manipulate variables, run scenarios, and observe the outcomes. It's like having a mini gas giant inside a computer. These tools, however, don't work in isolation. They complement and enhance each other. The telescope observes, the spacecraft probes and collects, and the computer simulates. Together they paint a more complete and intricate picture of the gas giants. Each tool adds a piece to the puzzle, slowly revealing the secrets of these massive planets. Yet, despite all these tools, studying the interiors of gas giants remains a formidable task. These planets are not just physically distant, they're also complex and dynamic, with many mysteries still hidden in their depths, but that's what makes the quest so exciting. Armed with these tools, scientists embark on a challenging journey to understand the interiors of these celestial giants. The journey to the core of a gas giant is fraught with challenges. It's akin to venturing into an alien world, a world of swirling clouds, extreme pressure, and scorching temperatures, a world without a solid surface to anchor our probes. Let's imagine this journey. As we descend into the gas giant, the pressure increases exponentially. It's like diving deep into the ocean, but with pressures million times greater. At these extreme pressures, even gases behave like liquids, creating what scientists refer to as metallic hydrogen, a state of matter that can only exist under such unfathomable conditions. We also encounter temperatures hotter than the surface of the sun. These high temperatures are generated by the immense pressure and the continuous gravitational contraction of the gas giant. It's a cauldron of heat and pressure, a crucible that tests the limits of our technology and understanding. Then there's the challenge of the absence of a solid surface. Gas giants are essentially massive balls of gas and liquid. Probing the interior of such a body is no small feat. There's no solid ground to land on, just an ever-deepening sea of dense gas and liquid metallic hydrogen. So, how do scientists overcome these challenges? They use ingenious technologies like radio wave tracking and magnetic field mapping. Radio wave tracking allows us to peer into the gas giant's thick atmosphere by tracking the radio waves emitted by the planet. This gives us a glimpse into the interior structure and composition of the gas giant. Magnetic field mapping, on the other hand, provides us with clues about the gas giant's internal dynamics. The gas giant's magnetic field is generated by the movement of electrically conductive materials within its interior. By mapping these magnetic fields, we can infer the movement and distribution of these materials, giving us insight into the gas giant's internal processes. Despite these hurdles, the journey to the core provides valuable information about the gas giants. It's a journey of discovery and exploration, a journey that pushes the boundaries of our knowledge and technology. It's a journey that, despite its challenges, continues to captivate and inspire us. By studying the interiors of gas giants, scientists can decode their secrets of formation and evolution. So how exactly does this work? Let's dive right in. The interior makeup of gas giants provides valuable clues about their birth and growth. By examining these behemoths, we can piece together their life stories, from their infancy to their current states. Two key theories help us interpret these tales: the core accretion model and the disk instability model. The core accretion model suggests that gas giants begin as solid cores which accumulate gas over time. Picture a tiny pebble in space, slowly attracting more and more dust, until it's a massive ball of gas. It's a process that's thought to take several million years, reflecting the slow and steady pace of celestial evolution. On the other hand, the disk instability model proposes that gas giants form rapidly. In this theory, a section of a disk of gas collapses under its own gravity, creating a gas giant in just a few thousand years. Think of it as a cosmic shortcut to planet formation. Both these theories contribute significantly to our understanding of planet formation. In fact, they're not mutually exclusive. Some scientists believe that both processes could occur, with the core accretion model explaining the formation of smaller gas giants and the disk instability model accounting for the larger ones. But why does this matter to us? Well, by understanding how gas giants form, we can gain insights into the formation of other planets, including our very own Earth. It's like having a time machine that allows us to travel back billions of years and witness the birth of our solar system. Furthermore, these theories help us comprehend the diversity of exoplanets we've discovered beyond our solar system. They allow us to predict what kinds of planets we might encounter in the future and where we might find them. Each discovery brings us a step closer to understanding our place in the cosmos. As we continue to study the interiors of gas giants, we're not just uncovering their secrets, but also getting to know our own planetary family a little better. But it's not just about understanding our past. Gas giants might also hold the key to our future. When we think about the search for life beyond Earth, we often picture distant exoplanets in the so-called Goldilocks zone. However, the moons of our very own gas giants could also be prime real estate for life as we know it. Let's take a tour of our solar system, shall we? Orbiting around Jupiter, the king of gas giants, is Europa. This icy moon is believed to harbor a vast ocean beneath its frozen surface. This ocean, warmed by the tidal forces of Jupiter's gravity, could potentially provide the right conditions for life to flourish. Then there's Titan, a moon of Saturn, another gas giant. Titan's atmosphere is thick and rich in organic compounds. It's almost like an early version of Earth before life emerged. It even has liquid lakes and rivers, albeit filled with ethane and methane instead of water. But who's to say that life, as we don't yet understand it, couldn't thrive there? Studying these moons and the gas giants they orbit gives us an invaluable perspective in the search for life. It helps us understand the variety of environments where life might exist, beyond the confines of our Earth-centric view. It's not just about finding water anymore. It's about finding places with the right chemistry, energy sources, and environmental conditions that could support life, even if it's radically different from what we're used to. It's also worth noting that studying gas giants and their moons can help refine our techniques for finding and analyzing exoplanets. The more we learn about the diverse array of celestial bodies in our own solar system, the better equipped we'll be to recognize signs of life elsewhere in the universe. So, the next time you gaze up at the night sky, remember that the gas giants are not just beautiful to look at, they are a crucial part of our quest to understand the universe and our place in it.